There's three basic types of exterior walls when it comes to facades. You have mass walls that you'll see on older buildings. The limitation with mass walls is when you get up above 16 stories, the thickness of the wall becomes so much that it's just not practical, and it becomes very expensive to go much taller than that. It's not uncommon for a 16-story building to have a wall that's 6 feet thick at the base. The theory behind a mass wall is moisture exposure on the outside penetrates the mass, and before it has a chance to reach the inside of the wall, just through sun exposure, it will evaporate the moisture back out of that wall. Now that process assumes that the mass wall is solid. And oftentimes we'll cut into a mass wall, and you can see in the photograph on the left there, you've got some hollow CMU here. You've got a hollow gap between the brick and the CMU. Here you've got a concrete wall and brick. There's a gap there. And so it really truly is not a mass wall. And you could likely have moisture find its way into the building. A barrier wall, as shown in the center detail there, was developed because mass walls were hard to use in high-rise buildings, and they're also quite expensive. And so with the advent of ductile iron and structural steel buildings and later reinforced concrete, they would try putting a barrier wall. And barrier walls could be precast limestone panels, the early forms of EIFS, and they're non-load bearing, and you're counting on one layer of trying to keep the water, air, vapor, and thermal temperature differences out of your building. And what we found out over time is that that's wishful thinking. More modern walls use what's called a cavity wall. Also, some people call it a drainage wall. This picture here is what's considered to be the perfect wall. There's cladding on the outside. Cladding can be anywhere from precast to brick to maybe even adhered masonry veneer. And then there's an airspace behind it. And so any water that, so the bulk water is taken care of by the cladding, but any water that, say, seeps in through the cladding will come into this airspace, drain down to weeps at the bottom of the wall. And then you've got your thermal insulation outboard of your structure. And then behind that, you've got your other control layers. You've got your vapor, air, and water control areas. That's the perfect wall. I mentioned thermal expansion contraction and moisture expansion contraction. You can see from the bar chart here that aluminum expands and contracts considerably more than steel, concrete, limestone, or brick. In fact, it expands and contracts 4 times that of brick and 2 times that of concrete, approximately. And so it's important to have sealant expansion joints between those materials, and the sealant joints got to be designed properly and have the right sealant to allow for the amount of anticipated movement, differential movement you're going to get between those materials. I mentioned moisture expansion contraction. Concrete and concrete CMU is the largest after it's cast. It's got a bunch of water in it, and water will disappear through hydration and also evaporation, and the concrete will shrink. By contrast, brick is fired in a kiln, and they fire off all the water, and so it comes out of the kiln, and it's the smallest it'll ever be, and it's just soaking up moisture after it comes out, and so it expands. And so you can see why in this particular case you would not want to rigidly attach the CMU to the brick. This is an example of some thermal expansion that took place on a project. And you can see a photograph here. Generally, you would have vertical joints in the brick every 25 feet on center, half of that distance up at the parapet because it's seeing the full extreme temperature contraction, temperature differential on both the back side of the parapet in the front side. And because this parapet was rigidly held by the returning end walls here, the wall actually buckled, and you can see the picture on the right. It buckled about 3 or 4 inches, and what helped it buckle was there is some flashing, through-wall flashing that served as a bond breaker that allowed this parapet wall to kind of lean over. And this was not uncommon design, 40 years ago, when not much was known about differential building movement. Also, 40 or so years ago, here's a brick veneer, again, with not the first joint in it. Normally, you'd have joints near the windows, within 2 feet of the corner. And you can see here on the right, this is where you have this wall on the left is expanding, contracting, and pushing out on the return wall. And what happens is it creates kind of a natural hinge. It cracks the brick there. This is a high-rise building project that we worked on in Atlanta, 34-story building. Built in the early 60s, before also, not much was known about expansion, contraction of different materials. You can see there's not the first joint in this wall. This happens to be in a courtyard area. Fortunately, people can't go in this area because this wall is essentially bowed from the top to the bottom where it's connected. The reason why it's bowed is the inner wythe is CMU, the outer wythe is clay brick, and it's got these turn bricks every so often that connect the brick to the CMU. And as we saw earlier, CMU is going to be shrinking its entire life, where brick is going to be expanding, and they're fighting against each other, and you try to attach them rigidly. And what happens is they break apart, and so it can only go in one direction, of course, and so it goes out. You can see this huge joint that people have tried to fill in with caulk. There's just a practical limit to how wide a caulk joint can be, and you can tell this didn't survive very long. The photograph on the right is actually taken with a remote camera that we were able to stick down in this hole, and you can see where the turn brick, you can see kind of the rounded edge of the turn brick, and you kind of see a concave section to the right of it. That's where that turn brick used to connect to the brick wall itself, and of course it's broken free. This is a picture of some moisture damage to brick veneer, and moisture, of course, typically gets in through the capstone here. You've got sealant between the pieces of capstone. That's an organic material. It's going to break down, subject to UV exposure, not to mention just old age, and allow water to saturate this wall. And when you get water in that wall, it deteriorates the face brick in a number of ways. One way is when this face brick is saturated and you get freezing temperatures, of course, water expands about 9% when it freezes, and there's no stopping it. So it'll bust the face off of face brick. The other thing that happens is just vapor pressure. When liquid in the form of saturation is heated up and becomes a vapor, it expands about 1,500 times its original volume, which results in about 4 psi or 600 psf of pressure. And there again, there's no stopping it. Another mechanism is related to osmosis, and that's when salts that occur naturally in building materials are picked up by moisture and travel through the brick, and then you get, they call it sub-efflorescence. And what happens is the water evaporates out the face of the brick, leaving the salt behind. And when that salt crystallizes, it expands in volume, and there too, it causes like 3,000 to 5,000 psi of pressure, and like I mentioned, there's no stopping it. The picture on the right is a capstone with some metal flashing on it, and somehow water is getting in there. It's either running through surface tension back underneath or getting in through the top, and that water, in this case, doesn't appear to be corroding, reinforcing, but it did manage to spall that concrete, possibly through freeze thaw. Speaking of corrosion, on the left is a picture of a relief angle. I mentioned that modern detailing has joints, every 25 feet or so in the face of brick. You also typically have relief angles horizontally at every floor level. And those relief angles, of course, are carbon steel. And when moisture interfaces with ferrous metal and you have oxygen, you're going to get corrosion. It expands about 6 times its original volume. There's no stopping it. And so in this case here, the expanding rusting shelf angle not only broke out the mortar between the joint here, but you see it broke out a piece of the face brick there as well. The picture on the right is a reinforced concrete beam around a screen wall for a cooling tower. Likely they didn't have enough protection on this rebar. There was not enough thickness of concrete or cover on it. Moisture reached the rebar, and you get what's called delamination, where you get a bunch of rebar corroding together, expanding together, and you get a whole face of concrete that comes off of the structure. Elastic deformation and creep. When you load up a material, all materials, they're going to expand and contract when the load is applied and taken away. That's called elastic deformation. When you put structures under a sustained dead load, that can cause what's called creep, which is more predominant in wood and concrete, but you can actually get creep as well in CMU and brick. And that's a long-term deformation that doesn't rebound. It's a permanent type of deformation. These two pictures here are examples of the building maybe creeping, and you didn't allow for that creep or movement of the building structure relative to the facade panels. You've got limestone panels on the left, and you've got terracotta panels on the right. And with the building either compressing elastically or through creep, put load on the facade, on the cladding that it was not intended to see or support, and you got buckling on both the left-hand side and cracking and buckling on the right-hand photograph. Another source of deterioration of building facades, I'm sure you've seen this on the news quite a bit. On the left, someone either mistook the gas pedal for the brake or drive for reverse. But for whatever reason, they drove through in this case, the storefront of a building. We've investigated quite a few of these. Sometimes they drive through pieces of precast or tilt-up concrete. On the right-hand side, you'll see something common at loading docks. You can see the dock seal on the right there, where a truck would back up and it forms kind of a seal around the perimeter of the rear opening of the truck. It looks like they didn't give too much room for the driver, so it's not surprising that a truck trailer impacted the corner of the brick. This is a little more rare, but we do see it, particularly at corners of buildings. Lightning seems to be attracted to corners. This is a piece of cornice at a project in Tennessee that got struck by lightning. If you look at the picture on the right and you look at the rope access technician that's standing on the remaining cornice, you get an idea how big this cornice piece was that fell to the sidewalk below that you can see on the left there. And that definitely would have killed somebody had it fallen on them. I suspect there's lots of facade failures of buildings that we never hear about or even investigate because no one was hurt or killed, or streets weren't closed. It just kind of got swept under the rug. Cracks can be caused by a number of mechanisms: differential foundation settlement, expansion contraction of walls with no vertical joints in it. One thing about concrete and brick is if you don't put joints in it, Mother Nature will put the joints in it for you. They just may not be where you want them to be. And so joints are also a place where water can get into the building. And so generally a masonry joint that's larger than about 0.005 inches needs to be filled in either with sealant or mortar, depending on whether the crack is still moving or not. On the right-hand side, you'll see some vertical sealant. There they did put an expansion joint in, but the sealant clearly failed in adhesion. It did not bond properly to the adjacent CMU, and then it looks like it was just simply painted over. To investigate a facade, do a facade inspection, it typically starts out with user interviews. The building engineer is a valuable source of information. They typically know the history of the building, where the problem areas are. They can help you find the existing drawings and any previous reports. That's part of the document research. You start out with a general visual inspection. It used to be done primarily with binoculars and a telephoto lens. Nowadays, with the invention or improvement of drones, we typically use a drone for this. We add a thermal camera that provides even additional information. We also look for watertight integrity at sealants, things of that nature. Classify the deficiencies, how serious they are and how quickly they need to be repaired. And we generate a report that includes an estimate. Starting out with the visual inspection, the photograph on the left used to be a picture of a couple tripods with one engineer on a telephoto lens camera, the other engineer looking through binoculars. And we were looking for anomalies in the exterior facade, places we wanted to look at close up when we did our hands-on inspection. Nowadays, that's been replaced by drones. We actually have a thermal camera on our drone that provides even additional information, helps us determine areas where insulation is weak, maybe there's a presence of moisture or air leakage from the building. Picture on the right is kind of a leftover from standing down below, looking at a building with binoculars and a telephoto lens camera. Looked very suspicious. Didn't matter how many times we checked in with law enforcement, they still showed up and we had to explain to them what we were doing. To do a hands-on tactile inspection, boom lift works the best, although there's a lot of applications where the owner doesn't want you driving on the grass. It might be the middle of winter. It may be a wedding style shape building where you can't get a boom lift with an extension long enough. In that case, we refer to rope access. We have certified industrial rope access technicians. The picture on the right is one of our senior level engineers that is he drilled a hole in a mortar joint and is looking inside the wall with a bore scope. On the right, this is another image of looking with a bore scope. You can barely see the boom lift there, part of it in the photo. But this is an engineer on a boom lift that's drilled a hole through mortar joint. And on the right, you'll see a image from a bore scope where you can see this is the adjustable brick tie, and you can see it's in real good condition, has not rusted or deteriorated at all. Cracks, you need to figure out if the cracks are active or static. If they're active, you would inject them, you treat them with sealant. If not, you could use mortar. You can put crack monitors on, as you can see on the left. You can take plaster and coat the crack with the plaster and wait a little bit to see if that cracks. Not all cracks need to be repaired. That's why we're measuring the crack on the right. Cracks in stucco, for example, that are greater than 0.013 inches are a problem. In masonry, it's as small as 0.005 inches is a problem. If you get cracks in concrete, reinforced concrete facades that are greater than, say, 0.035 inches, now you're getting big enough where you can have what's called aggregate interlock, and structurally, one side of the crack is not transferring load to the other side. In that case, the crack needs to be injected with epoxy. Sealant joints can be probed to see if they're reverting back to their original constituents. You can check the adhesive bond between the sealant and the brick substrate. Probing it is a good method for checking sealant. On the right, you've got a rotary hammer. You could use a regular hammer and tap on the concrete. In this case, it's a concrete structure. But a rotary hammer, you can cover a lot of area in a short period of time. In the old days, we used chain drag, which you drag a chain across a concrete slab and listen for hollow sounds. That only works on horizontal surfaces. But with a rotary hammer, you can check horizontal surfaces as well as vertical and overhead, and do it in a fraction of the time. I mentioned thermal imaging. This is a thermal image of a project in Atlanta, and you can see the colder areas of the thermal image. That's actually where air is leaking out of the building. So there's not a very good air control layer there.